When you observe your surroundings, you can note that there are some substances as hard and tough as a car, whereas some material like water can flow and have no definite shape. Why do different objects have different properties? Let's explore. In the previous topic, matter and its properties, we studied that books, pencils, school uniform, water bottles, balloons, precisely anything which occupies space and has mass is matter. All matter has unique properties. Objective: to study some of the properties of matter, we will start with a pencil. Try to bend the pencil. Can you change its shape? No, you can't. If you try harder, it will break. Your books, pencil and school uniform have a fixed shape, size, and they occupy a definite space called volume. Let us now turn to your water bottle. If you pour the water from the bottle into a glass, it takes the shape of the glass. However, the amount of water remains the same. Thus, water or any liquid for that matter has a fixed volume but no definite shape. On the other hand, the gas which escapes out on deflating a balloon mixes with the air outside the balloon and thus has neither a fixed shape or size nor a fixed volume. In general, all the substances can, in fact, be classified as the three states of matter. We call solids, liquids, and gases. But how are they different from each other? To answer this question, let us view the pencil, water in the glass, and air in the balloon very closely. We can clearly see that all of them are made up of small lumps of particles called molecules, arranged in different patterns. We will study each one of these patterns which differentiate the three states of matter at a molecular level in subsequent topics. To summarize, we have studied that the three states of matter are solids which have a fixed shape, size and volume, liquids which have a fixed volume but no definite shape, and gases which have neither a fixed shape nor a fixed volume. It must be clear how different states of matter vary in their observable features. But why do solids have a rigid shape and fixed volume? Stay tuned with us to find the answer in the upcoming video.
It's engineered to trap gas atoms and cool them to temperatures just a hair's edge above absolute zero. When it gets this cold, a curious state of matter called a Bose-Einstein condensate comes into existence. This isn't your classic solid, liquid, or gas, but an ultra-cool state of matter that behaves like a wavy superatom. Making them in space is an opportunity to hold a magnifying glass to the quantum world, but only for a brief period of time.
It is incredibly challenging making something ultra cold because there is nothing in the natural world that wants to be ultra cold. Something like this is so rare, so unnatural, so unlikely that you're talking about the coldest spots in the known universe.
The quest for colder temperatures has gone on for over 100 years. Scientists kind of steadily working to get colder and colder temperatures.
And by cold,
We're talking seriously chilling. Nanokelvin is a billionth of a degree above absolute zero, and picokelvin is now a trillionth.
strange and curious things happen when we get atoms to ultra-cold temperatures. But to understand why colder regimes are an exciting playground for scientists, we have to wade into some quantum mechanics.
Quantum mechanics tells us that everything has both a particle and a wave nature to it. And so at normal temperatures, atoms just kind of act like little billiard balls.
As we cool a gas of atoms, we lower its momentum, and each particle's wave nature starts to become more and more pronounced.
And if you get cold enough,
These wavelengths get so large, these atoms really start to blur together.
And at that point, this strange new state of matter occurs called the Bose-Einstein condensate. Bose is the person that really came up with the breakthrough to show that particles called bosons behave in this collective way. Einstein predicted that this state of matter would exist, but he thought it was at such a ridiculously low temperature that you would never be able to actually observe it.
this was back in the 1920s when quantum mechanics was the new revolution on the scene. They didn't have the technology to wrangle atoms just yet, but eventually,
Understanding quantum mechanics gave us lasers, semiconductors, transistors.
In the 1980s, people discovered ways to actually use lasers to cool atoms to incredibly cold temperatures. Most people's intuition is that you shine a bunch of lasers on something, it makes it hotter.
but by tuning a laser to a particular resonance frequency, scientists can slow down the motion of an atom, which essentially cools it.
Then in the 90s, people started developing these techniques to move those atoms into magnetic traps and then use this other technique called evaporative cooling to get to still colder temperatures.
Evaporation relies on losing atoms. You need atoms to go away to get out of the trap and carry energy with them.
After decades of technical progress, teams finally made Bose-Einstein condensates in the lab. They lasted inside a trap for a glorious 15 to 20 seconds.
It was clear that gravity had a big effect on these systems, and it would be interesting to do these types of things in space, even though it was totally crazy to even think about that. We're confining them with magnetic fields, and the magnetic fields themselves are changing and perturbing the atoms. So we would like to turn off the fields and just study the atoms on their own. But of course, in gravity, they just kind of go plop.
And that's why putting a lab in space offers a unique advantage.
You can shut the trap off and these matter waves remain floating.
We think we can get to a new regime of even colder temperatures for even longer amounts of time and make really sensitive measurements.
And that's where this engineered quantum mechanics box comes in.
CAL is a multi-user cold atom lab within the International Space Station.
The heart of it is this, what we call the science module. And then inside that, there's a vacuum chamber. There's computer to control everything and to store the data. There's electronics to drive magnetic field coils. And then there's a whole suite of lasers. We have two species that we're trying to trap, both rubidium and potassium.
The reason we like to cool those is because they've got one electron in their outer shell. You want to be able to continually drive excited state, ground state, excited state, ground state while you cool these atoms.
So we have this little small vacuum that has this little atom chip on top of it, and then that's mounted inside an assembly that steers all our laser beams.
For cold atom physicists who are used to tweaking their experiments, building a lab that could operate remotely was a huge milestone.
We sometimes call that last phase of a mission the death march. We had a number of issues that last few months, and things broke that we've been working with in the lab for decades and never had one break. This has sort of been my baby. It's something I've been working on like 20 years pretty much. To finally see it all together was just, wow. It was something that was amazing to go through and wonderful to go through, and you don't want to do it again.
The instrument is placed near the center of mass of the ISS. That's important for the gravitational measurements that we eventually want this kind of technology to be able to do. But it's right next to the astronauts' exercise bike, and it's when you see these videos of the shaking that's going on nearby.
So it runs during the crew's sleep periods. When these LED lights switch on,
We make the sample, and then we release it. We snap off our magnetic fields. The gas will start to expand.
You shine in a final laser pulse that blasts the cloud apart, and then you collect this light that includes the shadow of the atoms on a CCD camera behind them. And then tens of microseconds later, you send in another pulse that's a reference image. You subtract the two, and you get a density profile of the atoms that were there. We're always anxious to see as soon as possible the images coming down.
To detect that it's a Bose-Einstein condensation, there's certain signatures that you look for. It's a very sharp transition. Virtually every day we go down there and we turn it on and we run a sequence to make Bose-Einstein condensates. We're sending up an upgrade for Cal, and the new capability is going to allow us to have something called an atom interferometer, which is a really amazingly sensitive sensor for things like accelerations and gravity. And this is probably, in the long term, the most important thing to come out of using cold atoms in space.
Interferometers are sensitive tools that use the wave-like nature of atoms to make precision measurements of a given environment. They're great instruments to tackle some of the universe's most stubborn mysteries.
Some of the teams are going to do studies of Einstein's equivalence principle. The Apollo astronauts, did the first one of those in space. They dropped like a hammer and a feather and showed that on the moon. They fall at the same rate. We're going to drop a rubidium atom and a potassium atom. We can read them out with laser beams using this atom interferometry technique. As a general rule, you should never bet against Einstein, but there is this fundamental conflict between his theory and what's called the standard model of quantum physics.
And if there's a problem, that problem can be all the way back in the assumptions that the theory was built on. Einstein's equivalence principle is a fundamental tenet of general relativity. You're testing this fundamental tenet of general relativity with quantum mechanics.
Another experiment that I really like is trying to study the quantum nature of collisions. It gets to one of these, I think one of the really profound questions in physics is the basic laws of physics. Simple. We have just a few fundamental particles and they interact by these few simple rules. And they also tell us that in this whole universe, the only thing that's happening, really the only thing, is particles are coming together, they're colliding, they're bouncing off. Sometimes they change from one type to another. Sometimes they just go off in different directions. But that's it. And then how do we get this complicated universe that we see around us from that simple underlying physics? I think it's going to be really important and again, a kind of an iconic experiment if we